I am Dr. W.B. Gunure from Kamlanand Mahavidyalaya, Nagpur. Today we are going to discuss the methods to determine the composition and stability constant of the complexes, and two important methods are there. Number one is the that is job method of continuous variation, and second is the mole ratio method. Already we have discussed what are the factors affecting the stability constant of the complexes, that is nature of metal ion, nature of ligand, role of solvent, environmental factors, steric hindrance, and pH. So these are the different factors, and also chelate effect. So these factors affecting the stability constant of the complexes. And now two methods, important methods are there. One is a job method and the mole ratio method. These methods are used to determine the stability constant and the composition of the complex. Composition means whether the complex is formed by metal and ligand, and composition is 1:1 or 1:2 or 1:3, like that. So this composition of the complex can be determined by these two methods, and today we are discussing detail about these methods. So today's topic is the job method and mole ratio method, and these methods are used to determine the composition of the FeSSA complex, iron sulfur salicylic acid complex formation. And in this case, what is the first method is the job method for the determination of composition of the complex, and here the complex is iron 3 sulfur salicylic acid complex, and in this case spectrophotometric method are used to determine the composition of the complex in the solution. And example of the formation of complex is in general reaction. So metal metal react with the n number of ligand and forming the MElN complex. So this is general reaction, metal plus ligand forming the complex, and here the value of n can be calculated if the solution of metal and ligand are in equimolar solution. And here metal react with the ligand sulfur salicylic acid and form the complex in the acidic solution, and the formation of this complex is taking place in the pH range 2.6 to 2.8, and phenolic group and carboxylic acid group present in the ligand remain undissociated, and much of the hydrolysis of metal salt is increases in the range of optimum pH value. So we can say that metal ion react with the ligand and form the 1:1 composition complex, and this formation of complex is shown in the slide. And in this case, this is the metal Fe3 plus, and this is the sulfur salicylic acid having one OH and COH. Structure is shown here. This is salicylic acid, OH, and this is the position at 5 position, 1 2 3 4 5 sulfur salicylic acid. So this is sulfonic acid group, and they form H from this and H from OH and COH replace 2H and forming this type of complex ion. So in this method, so this is the reaction showing for the formation of complex ion, and this method is continuous variation and can be used to determine the composition of the complex as well as the stability constant of the complexes. This method is used for the solution where only one complex is formed. And for this determination of composition of the complex, we have to prepare the 10 solution and containing the metal ion and the ligand, and in the proportion and the total volume of the solution we have to keep it 10 ml, and this composition, that is the ratio of the metal ligand, is shown in this slide. This is the table which shows the ratio, that is the here serial number 10 solution we have to prepare. Volume of metal ion, that is Fe3 0 1 2 3 up to 9, and reverse of that 10 9 we have to take the ligand sulfur salicylic acid, and total volume we have to keep the 10 ml constant. So each total volume of each solution is a 10 ml. Therefore we can say that here now we see that sum of the concentration of the ligand and that of the metal ion is constant, and we can write the only the ratio we have to change. So in this way concentration of ligand plus concentration of metal is equals to C. C is the constant. So measure the absorbance of the solution. After making this 10 solution, we have to measure the absorbance of all the 10 solutions with the help of colorimeter or spectrophotometer at a fixed wavelength, that is known as the at lambda max. First of all, we should have to know the what is the lambda max, that is maximum absorbance at which what is the wavelength at which the maximum absorbance are taking place. In case of this complex, first of all we should have to find out the lambda max, means maximum absorbance at which wavelength is taking place, that we have to find out. After by taking any one solution out of 10, and we have to measure the at a different wavelength, note the absorbance, and the maximum absorbance showing by the solution the wavelength, that wavelength is the lambda max. So after after selecting the lambda max, then take the absorbance of all the 10 solutions, and then we have to plot the graph between the mole fraction of the ligand and absorbance, and the curve shown in the figure is shown here. This is the curve obtained for the plotting the graph between the here on this axis mole fraction, here is the absorbance, and the curve is obtained in this way. Maxima is there, but here is no any sharp maxima, so we have to extrapolate these two lines, this one and this is second. The point, this is the point of maximum absorbance. The two lines where they cross, this is the point at which the two lines cross, and this is the point which is the shows the maximum absorbance, and this is the point. This point also give the composition of the complex. So after this plotting the graph, from this graph composition of the complex can be obtained. If the complex is 1:1, then the maximum come at the middle here. If it is 1:2 or 2:1, then it is shifted to here from this middle, left side or right side. But now if it is in the middle at 0.50, then the composition of the complex is 1:1. And therefore when the in the next slide now shown, we say that when the legs of the curve are extrapolated, they cross each other at a point at which the absorbance is maximum. If the formula of the complex is mn, then we write n equals to, now here if the complex is a mn, we have seen the general reaction, so n equals to Cl upon Cm. Cl is the concentration of ligand upon concentration of metal. This equation can also be written as in this way: Cl upon C plus Cm upon C equals to C by C, that is the Cl plus Cm equal to C. So this is common taken way of C, so what is now is 1. With the help of equation, mole fraction of ligand, what is the mole fraction of ligand? Cl upon C. C is the total concentration of the metal and ligand. So by equation 2, from the equation 2, this equation 2 reduces to mole fraction equals to Cm upon C equals to 1. So here, so now Cm upon C real is this, so 1 minus mole fraction come to this side. Dividing equation 3 by equation 4, divide this equation 3 by equation 4, then we get Cl by C into C by Cm, then equals to mole fraction Mf minus 1 upon 1 minus Mf. So after rearranging this, we obtain this Cc cut, and Cl upon Cm equals to mole fraction 1 minus Mf. So this is nothing but the Cm, n. So n equals to mole, this we obtain the equation number 5. And equation number 5 used to know the value of n, and n can determine the composition of the complex. So by graphically and also by calculation, we can determine the composition of the complex. And in case of the iron sulfur salicylic acid complex, first of all prepare the 0.0002 molar, 0.0004 molar and 0.0006 molar metal salt in 100 ml volumetric flask having pH of 4.5, and from the stock solutions of 3 concentration of sulfur salicylic acid is also prepared accordingly in 100 ml volumetric flask of the same concentration by using the pH water 4.5. From the solution of different systems are prepared, absorbance of each solutions are noted at lambda max, and in this case lambda max is found to be a 510 nanometer. A graph of the absorbance versus mole ratio is plotted for all the 3 solutions which having same equilibrium concentration. The stability constant and composition of the complex is then calculated. The nature of the curve obtained shown in the figure, and this method of job method is known as a continuous variation method. This method is widely This method is widely used for the determination of composition of the complex. The resulting curve shows the maxima at the mole fraction corresponding to the stoichiometry, that is the composition of the complex. If the top of the curve is flat, extend both the arms, both the line, and the point of the intersection of the two lines give the composition of the complex. So this is the simple method, and that is, this method was given by Job, and this is known as Job method for the determination of composition and stability constant of the complex. But here we have seen the method of determination of composition of the complex by using Job method. Similarly, another method is there, that is known as the mole ratio method. This is very simple method as compared to the Job method, and this is the convenient and widely used method to determine the composition of the colored complexes. This method was given by the scientists James and the Yo. This method used to calculate stability constant of the complex. It is very simple method as compared to the Job method, and the difference between the two methods is that total concentration of the metal is kept constant. In this method, different system are also again we have to prepare as shown in the table. So thing is that here in the mole ratio method, the concentration or the volume of metal ion we have to keep constant. So here see, in all the systems the total volume of metal ion is constant. So again here we have to prepare the 10 solutions, 1, 2, 3, take the 10 flasks and number it 1 to 10, and take the 5 ml metal ion solution in all the flasks. After that add the ligand so that 1, 2, 3 up to 10 ml, and adjust this volume of water so that total volume of the system should be 25 ml. So after preparing by this taking metal ligand and water, and then we have to after making all the 10 system, the mole ratio method, different solutions are prepared which contain constant volume of metal ion and different concentration of the complexing agent ligand. The ratio of concentration should be vary from 1 to 10 ratio of metal ligand. First of all, find out the maximum wavelength. Again in this case, before going to note the determine the absorbance of the 10 solution, first of all find out the lambda max, that is wavelength at which the maximum absorption take place by taking any one solution. After measuring the lambda max, then record the absorbance of all the 10 solutions at fixed wavelength, that is at lambda max. The absorbance are then proportional to the equilibrium concentration of the metal ion present in the solution. After that we have to plot a graph between absorbance versus the mole of the ligand to the mole of the metal as shown in the figure. So here this is the figure which shows the plot between the absorbance versus the mole ratio of ligand versus upon this metal upon ligand, any ratio, one ratio we have to take an absorbance. So curve obtained in this way, so increases this mole fraction increases, and now here absorbance increases and then become constant. So here these curve give two values. One is when this curve is constant, this is known as AM or EM, and from the this is increases and then show the term. So this point is the ES. So from the value of ES and EM we know the value of alpha, and in case of now different cases are there. In case of here metal ligand ratio is found to be 1:1. Hence the empirical formula of the complex is shown here. If we have to consider when the complex, suppose complex is 1:1, so for that case this is the complex H form OH and H form COH, and this is the complex form. We have seen the reaction, and consider the formation of complex when metal and ligand is in the equilibrium. So here concentration metal plus ligand forming MLN. So concentration of metal is C alpha, ligand is NC alpha, and metal complex is a C1 into 1 minus alpha. So we know the at equilibrium constant K equals to concentration of metal product upon concentration of ligand. So we can write MLN upon M into N to the power N, because N is there. So put the value, these are concentration here, C1 minus alpha, C alpha is NC alpha to the power N, and where alpha is the degree of dissociation, and alpha can be determined by using this formula from the graph. So if you know the value of alpha, and alpha is obtained from the graph that we have seen the graph. So alpha is equals to EM minus ES upon EM. EM and ES is shown in the graph. So once EM is and ES, alpha is determined, put the value of alpha in the equation, we determine the composition and stability constant, where EM, what is EM now? It is the EM is the maximum absorbance in the presence of large excess of ligand, which suggests that all the metal bonded to the complex. ES suggests that it represents the value of absorbance when the metal and ligand are present in the stoichiometric ratio 1:n. When the metal and ligand are present in the ratio 1:1, then the stability constant is given by, for 1:1 complex. Now suppose if you take the 1:1 complex, metal and ligand are present in a 1:n composition, then the equation K equals to, this equation can be written as here, K equal to C 1 minus alpha, C alpha into C alpha. So after putting this value in the equation, what is then now here? Because here n value is 1, here also 1, we have taken 1, because 1:1, n is 1, so ligand is 1. So in this case, after 1 minus alpha, C can be cutted, and C alpha square, this is the equation. So by K equal to, K is the stability constant for 1:1 composition, stability constant by using this. So here in this equation, alpha obtained from this equation, and C is the concentration. So this is can be, by using this, the stability constant for 1:1 composition complex can be determined. Similarly, when the metal and ligand are present in 1:2, that is metal is 1, ligands are 2, n value is 2, the ratio, then stability constant can be determined by this equation. K equals to, this is C 1 minus alpha, C alpha, in place of n now we have to take the 2 C alpha square. 2, n is here, so 2, put the value of that. After cancelling the common term, what is then 1 minus alpha upon 4, and C square alpha cube, because C can see here, this C and 1 from the here denominator C can be cut. After that we obtain this equation. So by using again this equation for 1:2 composition of the complex, the stability constant can be determined for that iron sulfur salicylic acid complex. So these are the two methods used to determine the composition and the stability constant of the complexes. One is a job method, second is a Mohr ratio method. Mohr ratio method is simple as compared to job method, and by using this job method we know the composition, also the stability constant, and by using also Mohr ratio method, the particular composition of the complex, stability constant for 1:1, for 1:2, for 1:3, composition of the complex can be determined. So we have discussed today the two important methods to determine the composition and the stability constant of the complexes. And a complex here is the iron Fe3 plus combined with the sulfur salicylic acid ligand, and forming the complex of the type in general 1:n. So n may be 1, 2, 3, that is the composition should be maybe 1:1, 1:2, 1:3 for different composition, and by using these methods, job method and Mohr ratio method, we have to we can measure where we can calculate the, or we should know the composition and the stability constant. And in this method we have to use either colorimeter or spectrophotometer to know the absorbance of the solutions.